Okay, welcome back. Unit 5, Module 15. Today we are going to discuss certain type of process which are characterized in the frequency spectrum or in the frequency domain. So first one is called the band pass process, and band limited process is also a type of band pass process. However, its frequencies are strictly concentrated in a cluster of bands, and outside that band the power distributed for that process is 0. Similarly, we will also discuss another type of a band limited process. A narrowband process is a band limited process for which the central frequency, the modulating frequency or the central frequency of the band omega naught is very much larger than the bandwidth. Okay, so as we go, I will show you some pictures, and we will discuss the properties of each of these pictures. Now this is something that we have discussed in the last class, called as the product device, and normally it is used to calculate the product of a certain input process x of t and a carrier signal a naught cos omega naught t, where omega naught is a fixed constant. So if you remember that what we have spoken in the last class, so x of t is a random variable that is at the time t from the process capital X of t, and each of that variable at each time is multiplied with this cosine function cos omega naught t. Now the outcome of this product is another random process y of t, and this random process should have mean, because it is a random process. It should have it will have a mean of each random variable in the process, and also mean square value, autocorrelation functions, right, the PSD function. Similarly, right, all of these it will have all the temporal and frequency characteristics. Now y of t is a new process. Let us understand what is y of t here. How does it look like? Now all of you know how does a cosine of a certain frequency looks like. Cos omega naught t. Okay, omega naught is the angular frequency in radians per second, and normally we know it is a periodic function, right, with a period of 2 pi by omega naught. Now this function cosine at every time point is multiplied with a certain amplitude which is depending on the input process x of t, or in otherwise the amplitude of this cosine is modulated by this x of t. So at every time point the amplitude of this cosine is decided by decided by this function x of t. Now here that means this function y of t should be something like a cosine, but on top of the cosine there is a message signal. Okay, the amplitude of this cosine has that message signal x of t. Now sometime, yeah, so x of t is, as we called, it is sometimes called as the message signal, and cosine is called a carrier signal, and this kind of modulation is called as the amplitude modulation. So y of t is an amplitude modulated signal. Now and we know, yesterday we derived that the PSD, the power spectral density of a of this A modulated signal is of this form, where it consists of two copies of the PSD of the input process Sx, which are centered around omega naught, plus omega naught, and minus omega naught. Now, if you remember the picture, uh, let's say this is the PSD of the input process. Now, the input process, you can see here, is the power density is, the power is concentrated in a band of frequencies W, capital W, right? The width of this interval or this band is W, and all the power in the process is concentrated only in these certain frequencies, and outside these certain frequencies the power distribution is negligible, right? So in fact, this is the characteristic of real world signals such as audio signal, right, image signal, images, or any communication messages. All of these signals, they are normally low pass. That means the frequencies are concentrated near the lower frequency at around 0, right? So remember this. This is only the sample. This is one example of a power density spectrum of a input process x of t. Now, or inverts, this is the actually this is how generally the message signals, all the message signals will not have the same shape. This is only for simplicity purposes. We have made this diagram which shows the particular band of frequencies in which this PSD is concentrated. And so for a low pass, for a real time signals or real world signals, the messages or the message signals, as they are called, the power density is usually clustered around 0. Means they only contain lower frequencies, low pass, or sometimes it is called as the band pass, or baseband signals, because this is the band of frequencies in consisting of 0, baseband process. So any random process that has this kind of a characteristic power density spectrum can be called as a baseband process. Okay. Now this is the characteristic of all message signals in communications that we come across. Now the below diagram is shown the power spectrum of the output of the product device or the AM modulated signal, and we can see here that it consists of two copies of the same spectrum which are centered around the carrier frequency omega naught and minus of the carrier frequency omega naught. Okay, and its power is actually not the same. It is distributed among these two copies. Now this is the example of a process called as a band pass process. Okay, so you remember this one, base consists 0 frequencies, base frequencies, Now a band pass process consists of frequencies which are away from zero, which are distributed, which are clustered around a certain frequency omega naught. Okay. Now the frequencies that are concentrated around zero are negligible compared to the frequency, the power that is distributed around omega naught. So that is what. So that is what is called as a baseband process. Now let us come to the definition of a baseband process. It is a process which is denoted as capital N of T, and its PSD, as we saw, is clustered in a bandwidth of W radians per second, and usually this band of frequencies do not include omega is equal to 0 or the DC frequencies, low frequencies. Okay. So that is the clearly it is shown in the above diagram. Now similarly, what is a band limited signal? This is the kind of signal which has got certain simplification of the above process. It is also a band pass process, but whose PSD is clustered around omega naught, but outside the band of frequencies it has zero power. That means around zero, and the lower frequencies, the power at lower frequencies is actually zero for this band limited process. Okay, in the case of band pass, the power distribution at zero can be negligible. It need not be, but the power distributed at zero need not be equal to zero. There could be negligible power, but however that power should be small, should be negligible compared with the power in the bandwidth W. Okay, but whereas in the band limited process, it is also a type of a band pass process. However, the PSD outside the bandwidth W is completely zero. Okay, we will come to the diagram in a short while. But before we go further, now consider another third kind of a process. It is also a type of a band limited process. However, the bandwidth of such a process is very small, is very much lesser than the carrier frequency omega naught or the center frequency omega naught of each band. Okay, so if there is a clearly a peak frequency, then in that particular PSD, then we can consider omega naught as the frequency of that peak. However, if there is no clear peak, then we can normally take the closest frequency of the peak of that function. Now look at this. It becomes clear in this diagram. Now shown here, A is a band limited signal, or it is a band pass process. It is a power spectrum of a band pass process, and below is the spectrum of a band limited process. Now, as this is normally is the function that has negligible frequencies around zero compared with the power in this band of frequency W. So here, for a process to be band pass, the power near at zero or near zero need not be exactly equal to zero. Now look at the band limited process. The power outside, that is near zero, and all the frequencies near zero, outside this band of W, the power is completely zero. Now this is the characteristic of a band limited process, because normally it is a simplification of this band pass process, because normally in real signals, most of the power is distributed around the carrier, around this in this bandwidth W. But outside this bandwidth, typically, let's say 5% of that power can be cut off, can be made equal to 0, so that we can save these frequencies for another channel. Okay, so so a band limited signal is actually an abstraction of a bandpass process, in which the the power or the frequencies that have negligible power are completely made equal to 0. That means, okay, are shortened, the bandwidth is shortened in this band limit of W. Now, what is a narrow band process? Now let us consider, we said, what is the definition of a narrow band process? It is a band limited signal. That means its frequencies are clustered in a band of frequency capital W, radians per second, and outside this band of frequencies the power density is completely 0. That is a band limited signal. And for the band limited signal to be a narrow band process, the condition that must satisfy is that the bandwidth W, capital W, the bandwidth capital W should be very small compared to the value of omega naught. Okay, if you see, normally when we have a message signal, normally it is modulated with a very high frequency, right? So that is the circumstance that we are speaking here. So when W, or the width of this bandwidth, is very small compared to the carrier frequency, then we can call that such process as narrowband process. Now look at this example of a narrowband process, and normally this is the general abstraction for any narrowband process. Typically they follow this kind of a model. Now n of t is one variable in that process, and it is equal to r of t, which is another random process. Now we have looked at this kind of similar equation before also. A random process, we have looked at a similar random process before. However, this capital R is independent of time. That means it is only R, and this phase is also independent of time. That means what? For all times the random variable is the same, or in a way this is a more generalized version of that process, where at each time instant the amplitude is a different random variable, and also the phase is a different random variable at every time. So this is a more of a general EM modulated process, or it is a more general form of the equation that we have seen earlier. Okay, now so here R is a random variable and phi is a random variable shown in bold letters. N is also a random variable. Now for each time the random variables are decided in this fashion. Now if you look at, if W naught, which is a carrier frequency, is usually very large, it is a high frequency signal, and let's say in this diagram you can see that this is the high frequency cosine signal, although having differing phases at different times, that means the phase is also a fluctuating for this signal, and its amplitude is modulated by the function r of t, or r of t is sometimes called as the message signal. So whatever the amplitude of this cosine are being modulated, that means the amplitudes of this cosine are decided by the value of r of t. Okay, or this cosine takes the values of r of t as amplitudes. So in a way, this you can see here, this cosine waveform will have a amplitude shape which is overriding on top of this wave, and it is a low frequency wave. You can see that it is a slowly varying, a smooth function, and which is called as the envelope of this cosine. Okay, so the envelope of this cosine is this one, and the bottom graph. Now, what will be the power density spectrum of such a signal or such a process capital N of t? Now look at this. You can clearly see that the width of this in this diagram, the width of this bandwidth of this process is W, and it is very small. The width of W is very small compared to the total length of that, or the value of omega naught. Okay, now this is exactly shown in this diagram. Okay, now this is example of a narrowband process. So now we come to expanding this cosine as cos theta 1 plus theta 2, we can derive a much more useful form of this process, and which is very commonly used in communications, analog communications, and such an equation is much useful than what we have seen before. Now if I expand this cosine, and if I club this r of t and cosine of phi of t as another process x of t, I have this following form. That means n of t is equal to x of t times cosine omega naught t minus of y of t and sine omega naught t, where n of t is one process, x of t will be another process. As you can see that x of t consists of r of t as a process multiplied with another process. So this will be another third kind of a process which we call x of t. Similarly, r of t sine of phi of t is another process which we call a third kind of process y of t. Okay. Now it is once we have this relations, that is x of t is equal to r of t into cos phi of t and y of t is equal to r of t into sine phi of t, then we can normally derive these relations. That means if you square on both sides of these equations and then sum together, I will have x square of t plus y square of t is equal to r square of t times sine square of phi of t and plus cosine square phi of t. Sine square plus cosine square phi of t is equal to 1. Therefore, I can write r square of t is equal to x square of t plus y square of t, or in other words, in this form equation. Similarly, the phase phi of t can be calculated by dividing these two equations each other. That means y of t divided by x of t will be equal to tan of phi of t, or in other words, phi of t can be obtained as tan inverse of y by x, y of t divided by x. Now these relations are very useful, and normally this, as I told you, this equation has a more useful meaning, or it is much favorable for us to analyze such kind of a narrowband process. Now, we can actually, by using this equation, n of t is equal to x of t cosine omega naught t minus y of t sine omega naught t, we can derive certain properties in between these three kind of processes. That means what will be the mean of x of t, y of t, what would be the square of the mean of, or the mean square values of the process x of t. Similarly, what will be the mean square value of the process y of t, and how are these related with the mean square values of n of t. Then how are the autocorrelation functions related with each other? What is the form of autocorrelation function of x of t and y of t? What will be the cross correlation between x and y? Right? What will be the power spectral density of each of these processes? What will be the cross power spectral density of this process? All of these will be studied in the properties of the narrowband process. Now, narrowband process is also a band limited process. In general, this also applies for all band limited processes that can be expressed in this form. That means n of t is equal to x of t times a cosine with a frequency, carrier frequency omega naught minus y of t times sine of omega naught t. Now, what are the properties? Now, let us, for simplicity, let us make the assumption that the process n of t is a Whiteson stationary process, and it also has a zero mean. That means what? The mean of this process, that means the mean of the random variables at every time point is equal to 0. Then once we make such a simplified assumption, we can study the following properties of that process. So what happens if n of t is a Whiteson stationary? Then the individual process x of t and y of t will also be jointly Whiteson stationary. That means what? Jointly Whiteson stationary means three conditions. What are the three conditions? That is, x of t is Whiteson stationary individually, y of t is Whiteson stationary individually, and also jointly these processes, that means the the cross correlation of these two processes rxy is also only dependent on the time difference between these time points. So it is a function of rxy will be function of only tau. So remember, this is what is meant by jointly Whiteson stationary. Now, if the input process n of t or n of t is a zero mean process, then what is the mean of each of these process is equal to 0. That means the mean of x of t and y of t will be exactly equal to 0. Will also be 0. Now what will happen to the mean square value? What is this means? Now whatever this is, the mean of the square values of this random variable x of t. Now this t is for all the time. It is not for only time. Now this is for all the times we are calculating the mean square values of the random variables. Normally, the outcome of this is that we would have one average signal, we have an average of the random process. Now, according to this property, this means that the average of the random process, the average of the squares of the random process is all equal for all the three processes. That means for x, y, and n, the mean square of the random process is equal. In other words, the energy or the power, the energy of the random process for all the three process is same. Now look at this equation. What we have is, on the left hand side we have the autocorrelation function of x. So whatever it says is that the autocorrelation function of x is calculated by using this one equation. So now look at this one here. Whatever s of omega is nothing but the PSD of x. Sorry, this is actually, instead of v, this should be x, capital X. Now whatever this is the power density spectrum of capital X. Now we can see that the autocorrelation function is normally, for a Whiteson stationary process, is normally equal to the Fourier transform or the Fourier inverse transform of the PSD. But we have this following relation which doesn't have the complex exponential kernel that is multiplying this function. We have cosine of omega minus omega naught tau. So this is a particular, it is nothing but the Fourier transform. It is a simplification of that inverse Fourier integral, where we have replaced the complex exponential with this cosine. Now this happens when it is a simplification. It happens when this power density spectrum is an even function with respect to omega naught. That means at omega naught, if it is having a similar image, the identical image at omega is equal to omega naught on the other side, that the reflection of this right part of this PSD is same as the reflection at omega is equal to omega naught axis, then the simplification of that Fourier integral is this one. And we can see that the normalizing constant is actually 1 by pi, because we have changed the limit of this integral from, because this is an even function, we can say, so the integral of minus infinity plus infinity can be written as twice of the integral 0 to infinity. So applying those identities, we can obtain this equation. Now actually the proof of this, if there is sufficient time, I will also discuss in the next lecture. These are quite simple, but for now you can remember this, that whatever this means is that the power density spectrum is an even function with respect to omega naught. So the example of this can be seen in the diagram as well. Now look at any of these diagrams of the PSD. Now you can take this example or the very first example, much clear. This is the PSD consisting in this bandwidth of W, and normally here with respect to omega is equal to omega naught, you can see that the reflection of the right half of this function is exactly equal to this side. It is an even function with respect to omega is equal to omega 0. When you have this type of a characteristic PSD, then we can simplify the inverse Fourier integral in that fashion. Okay. Now the fifth property tells us that the autocorrelation functions of x and y are identical to each other. They are not different. Okay, so that is a bonus for us. So we can only determine one of these autocorrelation function to decide the other one. Now what about this cross correlation function? This cross correlation function is similar to the property 4 that we have studied now. Now whatever this says is that if the autocorrelation function is actually an odd function, okay, is an odd function, with respect to omega is equal to omega naught. Then the inverse Fourier integral simplifies to this format. We will come to the derivation in the next of these two properties. We will derive this in the next lecture. But now the autocorrelation function, the cross correlation function, that is R by X. Here the sequence is inverted. Then we have to normally the cross correlation function, when this happens, should be a Rxy of minus tau. But because of this property, you can see that the outcome is this one, that is the cross correlation function is actually an odd function. That means the reflection of this function should lead us to a negation in the front. It should be so Rxy is an odd function. So Rxy is an odd function, and also the value of this cross correlation function at delay is equal to 0. That is, tau is equal to 0 is exactly equal to 0. In other words, by substituting in the above equation, we can also say that because Ryx will be equal to minus of 0, I will have this following result. Now, so the ninth property tells us that the PSD of X can be computed as a low pass component. So LP means it is an operator which only extracts the low pass components, low frequency component of the entire PSD. Okay, so this should be read as that the PSD of the process capital X is equal to the low pass components of this expression inside this square bracket, where this is the two copies of the process capital N. Now similarly, the PSD of y of t, because we have seen that the autocorrelation of both of these processes are identical to each other. That means you take the Fourier transform of the autocorrelation, we get the PSD. So in fact, this is also true. That means the PSD of the capital X, capital Y are both equal to each other. Now, this is the cross power density spectrum, and normally can be computed as a imaginary number times the low pass components of this spectrum, this PSD. Okay, so it is somewhat similar to the ninth property. Now similarly, we also have, if you reverse the sign of this, the sequence of this xy, then we have to add minus in the front of sxy. Okay, if you change this order, then minus comes in the front. So now these are the 12 properties of this band limited process or band limited processes. Thank you very much.